Hi everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about non-Newtonian fluids in CFD. So just to give you an overview of what I'm going to talk about today, I'm going to start by talking about how do CFD codes model non-Newtonian flow. I'm then going to look at why is special treatment required for fluids which have a yield stress. And then finally, I'm going to finish off by looking at what if the flow is locally non-Newtonian in some areas of our mesh where the rest of the flow may be Newtonian in behavior. So to start things off with a recap of what you may have seen before in your CFD and fluid mechanics lecture notes and courses, non-Newtonian flow behavior is usually presented in the form of a graph of shear stress, tau, against strain rate gamma dot. And if you look at the example plot on the left there for a Newtonian fluid, we see that the shear stress tau varies linearly with the strain rate gamma dot. And as the flow varies linearly there, the gradient gives the dynamic viscosity mu, and this is typical of a Newtonian fluid. Now, if we have a non-Newtonian fluid, then the variation of shear stress tau with gamma dot is going to take the form of a non-linear function. And the image there in figure B just gives you an example of one type of non-Newtonian flow behavior you might see. Now, in your courses and lecture notes for fluid mechanics, the reason you see non-Newtonian flow behavior presented in this form here is because the data is usually derived from experiments, and this is the most convenient form to present the data that was derived from those experiments. So just to give you an example of these experiments, what might typically happen is we have a thin layer of fluid between two plates, and the top plate is moved with some applied force F, and that generates a velocity profile between the two plates, as you can see there in the diagram. And if the layer of fluid is thin, we get a typical Coyette flow profile, which is linear. And what this experiment allows us to do is the force applied to the plate, we can divide by its area to get the shear stress, and then we can measure the velocity profile and use this to calculate the strain rate. And what we do for the experiments is move the top plate with a variety of different forces and each time measure the strain rate, and that gives us some data points which we see there on the left. And then we perform some curve fitting exercise, and that allows us to establish the behavior of the fluid, whether it's Newtonian or non-Newtonian. And of course, for these experiments, rather than using two parallel plates, you could use two discs. You could use a rotating disc and a stationary disc, and in which case we'd be measuring the torque rather than the force applied to the top disc. Now, in the Navier-Stokes equations that we solve in CFD, it's important to remember that we need a function for the dynamic viscosity mu, which is highlighted there in red. So from the previous graph, you might remember that we presented shear stress against strain rate. However, those two quantities don't appear in the Navier-Stokes equations, and what we need is the dynamic viscosity, which was the gradient of that curve for a Newtonian flow. So we're going to need to do some sort of manipulation if we want to use this fluid model in our CFD code. Now, for a Newtonian flow, as I just mentioned there, what we can do is we can take our experimental data and take the gradient. That gives us the dynamic viscosity, which we can then use in our Navier-Stokes equations. And the important thing to remember from this curve is that because the gradient is constant, the dynamic viscosity is also a constant, and it doesn't depend on the strain rate gamma dot. Now, this will be different for non-Newtonian flows. If we have a non-Newtonian flow, the conventional approach is to define an apparent viscosity, which is given the symbol eta there. And it's very important to note that the apparent viscosity is the shear stress divided by the strain rate at a single point on the curve. So it's not the gradient. There's a subtle difference there. And what we would do is if we take our experimental data there on the left and we pick off a point on the curve, we read off the shear stress and the strain rate, divide them, and that gives us our apparent viscosity eta. And if we plot eta, we find that the apparent viscosity is a function of strain rate. So we're going to have to use a slightly different treatment in our Navier-Stokes equations when we use our CFD code. And the first change that we make is that in the Navier-Stokes equations, we replace the dynamic viscosity mu with the apparent viscosity eta in the two terms which you can see highlighted in red there. Now, really when you think about this, this is just a change of notation. At this stage, nothing has happened and the treatment is not any different for a Newtonian or a non-Newtonian fluid. The only difference is that the apparent viscosity eta is going to be a function of the local strain rate at a given position in the mesh. And I'm going to go in a little bit more detail to show you how we calculate that local strain rate. So before we do that, there are a few models which we can use for the apparent viscosity of a non-Newtonian fluid. And one of the most popular forms is a power law, which you can see there in equation 4. And with the power law, the shear stress tau is related to the strain rate gamma dot by some factor k, and then the strain rate is raised to the power n, so it's a power law. And the value of the power law index n gives the shape of the curve. If we have a value of n greater than 1, then we have a shear thickening fluid, which is given by the red line there in the diagram. If we have a value of n less than 1, then we have a shear thinning fluid. And you may also have noticed that if we take a value of n equals 1, then we return to a Newtonian fluid, as we saw before. And in this case, if n equals 1, you substitute that into equation 4, then we get that tau is equal to k multiplied by gamma dot. And we can see that k, which is often termed the consistency index in the user manuals of various CFD codes, is actually equivalent to the dynamic viscosity if we were modeling a Newtonian fluid with a power law. Now, if we want to get the apparent viscosity, what we need to do for the power law profile is divide equation 4 by the strain rate gamma dot. So not differentiating, we're dividing. It's very important to remember that. And so what we see is we get equation 5, which is the consistency index multiplied by the strain rate to the power of n minus 1. So if you ever see this formula appearing in your user guides and you wonder why does the n minus 1 appear, it's because we're dividing by the strain rate gamma dot. We're not differentiating there. So how do we get the strain rate in our mesh? Because now for our CFD code, the apparent viscosity is going to be different in all the cells in the mesh, and it's going to vary depending on the local value of the strain rate gamma dot. And you may have noticed at this point that the apparent viscosity eta is a scalar value, and therefore the strain rate also needs to be a scalar value. Now, in order to get the strain rate, what we need to do is we need to think of the velocity gradient at a point in the mesh. So if you look at the very simple diagram I've got for you there, we've got a collection of cells, and at the cell centroids, where we store the information for the flow variables in our mesh, we have a value of the velocity gradient. Now, remember that the velocity has 3 components, u, v, and w, and it also varies in 3 different directions, x, y, and z. So actually the velocity gradient is a tensor quantity or a 3x3 matrix, depending on how you like to think about it. So we've got this 3x3 matrix there in equation 6, and we'd like to return to a scalar value for the strain rate so that we can then calculate the apparent viscosity. So how do we do that? The equation that we use is equation 7, where the strain rate scalar is equal to the square root of a half times the double inner product of the velocity gradient, which is given there by the colon operator, which you may see in some of the user guides and the CFD manuals. So what does this double inner product mean? Because it might not be an operator that you come across often. Well, the way that we can understand the double inner product is by first thinking about the vector inner product, which is given by the central dot. And if we look at equation 8, if we have two vectors, a and b, then the inner product of those two vectors is just each of the components multiplied by each other and then summed. So a1b1 plus a2b2 plus a3c3. And if we were to take the double inner product of a 3x3 matrix, it's very similar. All we do is we multiply each of the individual components by their corresponding individual component in the matrix and then add them all up. So it would take the form of equation 9 there. So a double dot b is equal to a11 b11 plus a12 b12, etc. all the way through. So the matrix double inner product will again give us a scalar value, and that's what we use to calculate the strain rate. So really, to bring that point home, the strain rate scalar is going to be equal to the square root of half times by the velocity gradient, each component multiplied by itself and then added, because the vectors a and b are the same. And what that means is that for every cell in our mesh at the centroid, because we have the velocity gradient, we can then work out the strain rate scalar using equation 10 and then plug that into some form of power law or any other function of gamma dot that we might have and use that to calculate our apparent viscosity eta. And then we can put that into the Navier-Stokes equations for our CFD code. So now I'd like to move on to talk a little bit about yield stress. Now, some non-Newtonian fluids, such as Bingham plastics, exhibit a yield stress, which I'm going to denote by tau subscript naught. Now, just a reminder, what is a yield stress when applied to a fluid? What a yield stress is if we apply a force or a stress to the fluid in our experiments, the fluid will not move unless that stress exceeds the yield stress. So how we can think of this is if we apply a very small force in our experiments, the fluid doesn't move and it behaves like a solid. But if we apply a large enough force, the fluid will start to move and may behave like a Newtonian or a non-Newtonian fluid. Now, to give some examples of this, some household examples you may find would be toothpaste or ketchup. If you have your tube of toothpaste, initially it behaves like a solid, but when you squeeze the toothpaste with enough force, the toothpaste will flow like a liquid out of the nozzle and then again behave like a solid because a shear stress is not being applied to it. And the way we represent this with a graph is something similar to that which I've given on the slide. So you can see that for shear stresses less than tau naught, the strain rate is 0, and so the fluid won't move at all. Now, if we want to incorporate this behavior into a CFD code, we need some special treatment, which I'm going to go through in the next few slides. So firstly, how could we represent this mathematically? A very common form you'll see for a Bingham plastic is given there in equation 13. So the shear stress is equal to the yield stress, tau naught, plus the apparent viscosity times by the strain rate, gamma dot. And again, to get the apparent viscosity, we divide by the strain rate, and that gives us equation 14 there. And that seems fine for us at the moment. However, if we think about it, what happens to equation 14 when the strain rate in the cell is 0? And this may happen, for example, if we have a uniform flow, when the velocity gradient is 0. If there's no velocity gradient, then the strain rate is 0, and equation 14 would result in a divide by 0 error, which is definitely not good for our CFD code. So we have to use some special treatment to get around this divide by 0 error when we have a yield stress. And the way we do this, one possible way you can do to get around this is to introduce a limiter into equation 15, and how this might look is the form given there in equation 16. So the value that we take for the strain rate will be the maximum of the actual strain rate and some limiting value gamma dot naught. So what this means in practice is that the curve which you can see there in the figure, if we're below this critical value gamma dot naught, then actually what we're doing is applying a linear profile between 0 and the cutoff point there. So what that means is we won't receive a divide by 0 error, and the CFD code can proceed with its calculations. But if we think a little bit more carefully about what's actually happening in this figure, then if our strain rate is less than gamma naught, we can see from the figure there that the gradient is actually really steep. And if the gradient's really steep, that means that the apparent viscosity, tau naught divided by a very small value, will be very large, but it won't be infinite. So in practice, in those few cells in the mesh where we would normally be receiving a divide by 0 error, in this case we just have a very high value of viscosity, which means effectively the fluid won't move, or it'll be very resistive, much like a thick sludge or slurry. Now, just to finish off, I'm going to proceed to talk a little bit about multi-phase flows, which is one example of a type of flow where we may have some regions of locally non-Newtonian flow and otherwise globally Newtonian flow. So just a very simple example for you to think about is if we have water and some sludge or mud in a pipe, for example, that you can see there in the picture. We may have water at the top, and then the sludge and the solid particles sink to the bottom of the pipe there to give a sort of sludgy, non-Newtonian region at the bottom. And we expect the water at the top to behave with a Newtonian behavior, and the sludge at the bottom to behave with a non-Newtonian behavior, probably with a yield stress. And in CFD, of course, this would be represented with the grid that you can see there at the bottom, with blue cells with mostly water or a high mass fraction of water, and then at the bottom where we have sludge, we have a much higher mass fraction of sludge. And the way we incorporate this into our non-Newtonian fluid model is that we have the yield stress, tau naught, and also the apparent viscosity there, eta p, being functions of the solid's concentration, x. So what that will mean in practice is that in our mesh, for areas where the solid concentration is very low, that means we've got almost entirely water, then the apparent viscosity will reduce to the Newtonian viscosity. And in areas where the sludge viscosity is very high, then we expect our apparent viscosity to exhibit a yield stress and to have a very high plastic viscosity value. So that may seem a little complicated for you, but I think if you just have a quick look at the figures there down below, it should help you understand a little bit more. So if X is the solid's concentration now, so not the strain rate, this is the solid's concentration. If the solid's concentration is 0, we see that the yield stress is 0, so we don't have any yield stress behavior, and the apparent viscosity is the apparent viscosity of water there, so eta sub W, which is dynamic viscosity of water. So we have no solids, we're at the top of the pipe where we're entirely water, and equation 17 there will just reduce to the dynamic viscosity of water. Now, as we go towards the bottom of the pipe, our solid's concentration X gets very high, and we can see there that the yield stress will increase. So we're going to have a yield stress, we're going to have some form of plastic behavior at the bottom, and also the plastic viscosity there is going to increase. So the local dynamic viscosity is going to be increasing, and so the fluid will behave much more like a sticky sludge at the bottom. And by carefully choosing these models, by calibrating them, hopefully some experimental data which you may have, you can actually develop quite an elaborate model for the non-Newtonian and Newtonian flow in a pipe or similar geometry. But I'm not going to go through those in any more detail here, and leave that to yourselves to have a look through for whatever application you're looking at. So just to finish off with a quick summary of what I've talked about today, just a reminder that at the cell centroid, for every cell in the mesh, we have a scalar strain rate, and this scalar strain rate is calculated from the velocity gradient tensor by taking the double inner product. Once we have that strain rate, we can calculate the apparent viscosity using the power law there in equation 19, or another appropriate non-Newtonian flow law there, perhaps calibrated to experimental data. And then that apparent viscosity there is going to be increasing the strength of the diffusion term in the Navier-Stokes equations, and that's how the non-Newtonian flow behavior enters the Navier-Stokes equations there for the CFD solver. And finally, remember that for non-Newtonian flows that exhibit a yield stress, we always have to have some kind of special treatment to prevent a divide by zero error when the strain rate is zero. And one example which I gave you here today was just a simple limiter, which is a switch to ensure that the viscosity would be very high, but it wouldn't be infinite in those few cells in the mesh. And I'd just like to finish off by, as always, thanking all of you for continuing to support my channel. I really do appreciate it. I look forward to hearing all your comments in the description below. If you have any questions which you'd like answered, perhaps parts of this talk that weren't explored clearly enough, or anything you'd like further information on, feel free to just leave them in the comments below, and I try to get to all my comments as quickly as possible. And the next thing I'd like to talk about as well is if you'd like to support the channel, there are a number of ways you can do this. You can support through Patreon, leave a donation through PayPal, or even just buy me a coffee in the links which you'll see in the description below this video. And I'd also particularly like to thank my 2 patrons for supporting the channel. I really do appreciate it. Thank you guys very, very much. I really appreciate it. And one additional benefit you guys get from following me on Patreon, of course, is that you get access to all of the PDF lecture slides that I use here in the YouTube talks. So if you'd like to get the PDFs to print them, have a look at them in your own time, and maybe go through them in a bit more detail, that's one of the benefits you can get from following me on Patreon. And at this point, once again, thank you guys so much for your support. I really do appreciate it, and I look forward to hearing from you.